Bismillahirrahmanirrahim. Assalamu alaikum everyone. As usual, I would like to start from the previous lecture summary. If you remember, nowadays we are going through the problems of estimation. It is very necessary to know about the problems of estimation, because if we are unaware of the problem, definitely we will be unable to solve those problems. So the first problem that a regression estimation face, that is the multicollinearity. In the previous two lectures, in detail, we went through the nature, scope, and etc. of the multicollinearity. I would like to just give you a smart and brief summary of that discussion. What is multicollinearity? Simply speaking, when our regressors that are the independent variable, when they are related with each other with exact relationship, it is called the multicollinearity. Multicollinearity, we are not concerned about the multicollinearity that it is it's present or not present, because it is always present there. But our concern about is that what is the degree of multicollinearity. If its degree is high, very high, for example more than 80%, then it is a big problem. But if it is less than 80%, we can ignore, or you can say this is the tolerable level of multicollinearity. What were the sources of multicollinearity? That why multicollinearity appears in the data? Many sources there. The first may be that there is a small range. The variable that are the independent variable, they are changing within a small limit, and ultimately there is the possibility that they are going to be multicollinear, or you can say the collinear. The other was that sometimes there is physical constraint in the data, in the population by nature. For example, if we are interested to see the electricity consumption of the houses, we regress electricity on the house size and the wealth and income. Definitely you are aware that the people who have more income, they have larger houses. So such kind of, there was that how it comes into the data. Then we talked about that how to detect it. Simply, if there is if there are two independent variable, we can draw on the picture. But when there are more than two variable, then we have to go through some systematic problem. And the more you can say, the important question was that if it is present in the data, then what the problem can appear. So the first and the theoretical problem was that if there is exact linear relationship between the independent variable, then we will say that our beta coefficients, that are the slope coefficients, they become indeterminate, and the size of the standard error becomes extremely large. But if it is high, although we can determine the coefficient of slope coefficient, but still there is very large variances, and you can say the standard error. And you are well aware that as the standard error increases, our confidence interval increases, and the probability of null hypothesis being accepted increases, and the t statistics becomes insignificant. The next issue we discussed was that how to, if it is present in the data, what are the remedial measures? Because you are only a good doctor when you diagnose the disease, and ultimately you give some suggestions, medicine dose, that this can be avoided in this way. So what we did, we said we discussed different techniques. For example, we said we transform the data. The other was that we drop one of the variable. So such kind of method, I am not interested to go into detail, but what I would like to say, the interesting thing is that our OLS estimator remain below best linear unbiased even in the presence of high multicollinearity. But the only issue is that standard error becomes large, and then there is a problem of, you can say, null hypothesis and the hypothesis testing. What we are going to do now today, our discussion will be very interesting and a bit technical. Technical not in a sense that will be using mathematics too much, but I will be giving you some of the example, and I will be telling you that how we have to deal with the problem of today that we are going to discuss, that is the heteroscedasticity. What is the heteroscedasticity? It is also a problem of the classical linear regression model. What are the problem? Immediately you should see that now we are creating the problem on ourselves. Why? Because in the classical linear regression model, we assumed many of the things. Now one by one we are lapsing these assumptions, and we are ensuring that what happens if this is not the situation. So you should be extremely careful while you complete your analysis. You will have to test all these statistics, whether there is multicollinearity in your data, whether heteroscedasticity, and if it is present hetero or any of the problem, you should go for some of the remedial measure. So first of all, we will see that what is the nature, followed by reason, why heteroscedasticity, and what are the consequences. Because if the consequences are not serious, then we can ignore to some extent, and then we will detect, because unless and until we are aware of that the heteroscedasticity is present in the model, we are unable to treat or address this issue. And at the end, as usual, it is our practice that we are not concentrating on the normative science. We are going something further, not positive science, but we will be normative science, and we will be presenting some of the solutions. So starting from that, what is the heteroscedasticity? Hetero means not equal, and scedasticity spread. If you go to the assumptions of the classical linear regression model, there we assume that there is homoscedasticity. It is totally opposite of the homoscedasticity, and when there is a heteroscedasticity in the data, we will be looking at this. So what is this? If the variance of the error term against the fixed values of the x is not constant, then we will be saying that there is a problem of heteroscedasticity. And simply speaking, if you see here that symbolically we write it that the expected value of ui hat square should be a constant. This is the homoscedasticity, and if I only write I here, it means I can change from 1 to n, then it becomes a problem of heteroscedasticity. So just I would like to give you a small diagram that will show that there is heteroscedasticity in the model. I am 100% sure that you know what is the heteroscedasticity, but as we are going in the detailed discussion of heteroscedasticity today, we will have to start from the very beginning, and I would like to show you that how the heteroscedasticity can be presented. This is three-dimensional diagram. This is a y. This is the function of u, as you know. This is, and this is the axis. If I show here, you will see that look at the spread. This is here. Now I deliberately on this x-axis, I am making it is a greater. You can make even small. And if I go further, I can make it in this way, that against this x, that is the x3 now, that is now it is of this kind. So this is the situation. This is the heteroscedasticity. Look at this. Here the spread is small. Here the spread is a bit larger, and it is a very large spread. So what we seeing that the variance of the error term is not constant at different level of, so the assumption of the classical linear regression model is lapsed. If I want to show you the homoscedasticity, I will be making the same spread equal, and I will not allowing the variance to change over time. Why heteroscedasticity? From where it comes? Because if you are aware of this, from that what are its sources, I am sure you will be plugging those loopholes and when you will plug many of the loopholes, you will be able to get good results. The first source of heteroscedasticity is error learning model. Every human being learns from his errors. So what we do, if we look at our previous history, I am thinking that you are now more than 20, and if you look at your previous, you are now more accurate and you have learned many things from your previous error. So now you are becoming more and more, you can say, the serious, more accurate, and you can now analyze the problems in a more concrete way. In simplest words, I say the margin of error has decreased. Similarly, when there is error learning model, after each error, after a group of errors, we learn and our errors are decreased. So this happens in many of the real phenomena. If I would like to give the example of that typing error, for example, if you start learning typing, I say that for example, in the first hour of your typing, you make 20 mistakes. In the second, there are less mistakes. In the third hour, there is also less. So the margin, or the spread of your error is decreasing, and this is based on the error learning model. There is a feedback and you are improving your capacity, and as the capacity improves, it brings down the spread, that is the cedasticity, or you can say this is the variance of the error term. So I am going to show it here, that how this is. Now these are your hours, these are your errors, this is the density, and these are your, you can say, the time. This is the first hour, and I can say that you were making much of this is, the variance was very high. In the next hour, this is hour number 2, you learn and it decreased, and if you are a good learner, in the third error, your variance may be very small. So this is the situation. The first reason why this comes, because there is a reality phenomena. Everything is, we are dealing here with the reality. We are abstracting information from the reality. We are not jumping in the air and we are talking about something abstract. We are trying to measure and mechanize the things, and here we are looking that the reality shows that a person learns from his previous errors, and as a result there is heteroscedasticity. Keep in mind that do not assume that every time heteroscedasticity the variance is increasing. Variance may decrease as you are looking here, and in some cases we will see that the variance keeps on increasing. So our purpose is not with the increasing or neither with the decreasing. Our purpose is either it increase or decrease. We only want that it should be constant. If it is not constant, whether it increase or decrease, we say that there is a problem of heteroscedasticity. The other reason is that the discretion and choice. You know, if your income is very small, you have less discretionary power to spend it. Or I can say that income is equal to, your income is Y is equal to C plus S. Either you consume or you save. So when your income is very small, for example, if I take only this function, that I say that the saving of function of Y. So I say that when your income is very small, then you have no discretionary power. There is discretionary power, not much discretionary power, that you can save more. But as the income increases, your discretionary power increases, and as a result, there is a change in the, you can say, the error of the variance of the error term. Other example I would like to give, the companies who have large profits, they have more discretionary power to give dividends to its stakeholders. Similarly, if you are in the bank and the bank is earning huge profits, then it has more power, you can say, that it can give bonuses to its employees. So for example, I am supposing that as the savings are the function of Y, that is the income, so as the income increases, the saving also increases, but not at the same ratio. The more at some level, when there is more income, the people save more. In the beginning, as the income increases, saving do increase, but not much increase. But after some time, you see that there is a huge change in income, and there is a huge change in saving. By the way, I am talking about the marginal propensity to save. So I would like to show it here. This is the density, and you can say this is again the similar. Now you will be looking that A will be increasing. I say that at this income, this is your saving, that this is at Y1 income level when you are not too much rich, and I am supposing that you are becoming a business tycoon like Malik Riaz. In the beginning, if I say that the savings of the Malik Riaz was this one, I would not like to mention it again. I would like that you are the Malik Riaz and you are becoming this. So in the beginning, this was the spread of the error term, very small discretionary power with you, but over time what happened? This is the Y2. At the Y2 level income, look at this, this may be 100, this may be 100 million, you can get it. I am not supposing the time, only a span of time 1 month or 2 months, it could be 20 years or even more. So this is when I would like, now look at this, it has increased. And when you are billionaire, not the millionaire, now you are billionaire, and look at this, this situation can occur. So what is this? Now the expected value of UI hat square is not a constant. Every time this is increasing. So this was the second reason. I will have to go to the third reason. Improvement in data collecting. If you go to the first one, there was error learning process. But here I am saying that improvement in data collection techniques. As the humanity is, you can say, the advancing, there are refinements in the technologies, in the machines, in the computer that helps the humanity in a more positive way. In the previous, as we are going through, look at, we started from the desktops, now there are laptops, tablet PCs and so on. महवे हैरत हूँ कि दुनिया क्या से क्या हो जाएगी. So what is this? Everything is improving. So there are methods of improving collecting data. So look at the banks. If you see that in the beginning, if you assume a bank, for example, up to 1980, the banks are 1990, the banks were mostly doing their business manually. So when you are doing manually, I think you can guess that there is a more error chance. But as there is development, there is evolution in the collection, or you can say the usage of machines and computer, now there is a very, very small margin of this, and indirectly I am saying that the error sum of square, or you can say the residual sum of square, is decreasing over time. So now if you look at this, for example, if I would like to make the bank, for example, this is, I say this is the MCB, and I would like to give it over time that what happened, this is, and this is again. So what is this? This is the time 1980. Banks were doing manually everything, and this was the variance of the error term. So when it came the 1990, now you can see there was some improvement in the data collection. Data collection, their processing or whatsoever they. And in 2000, I can say that it has suppressed, and now if it is 2013, I can even go one step further, that this is this one. So if you see that the variance is at this is higher, from here it is less, and it is further less. So this was the third reason, that says that over time there is improvement in the data collection methodology. The fourth reason is outlier effect. Now first of all, we will have to see that what is the outlier. Outlier is simply an observation that is much different from other observation, or simply you can say that this is observation from some other population. For example, if there are people averaging between 5 feet to 7 feet, and immediately one person comes with the 10 feet height, this is an outlier, because this person has come from some different, you can say, the population, maybe from Mars, if there is the population, I am not sure. But if it is some from any other planet and it has the 10 feet height, we will be saying that this is from the other population. Similarly, on the other extreme, I can say if a person comes only with half foot, then definitely it is also from the some other population. So if this is the case, such kind of case, then there is also problem of heteroscedasticity. Inclusion or exclusion of the outlier brings heteroscedasticity into the model. I would like to show you that what the outliers are. This is outlier. Look at this. If I say that I would like to show these are the observation, for example, any of the observation. For example, these are savings and this is income. And some person has such kind of one observation is standing here. So this is now outlier. This is totally different from the population. It is something different from the population, and as there is outlier effect, then there is a problem of heteroscedasticity. So this was the fourth problem. I am going one by one, and I will at the end show that heteroscedasticity is a huge problem and very critical problem as compared to the multicollinearity. So it is not a time to discuss that what was there, what is happening here. I would like to go further, and then I will flash back on this issue. So this is, if there are outliers, then there is a problem of heteroscedasticity. Specification bias. In the classical linear regression model, it was our assumption, I think that it was the last assumption, that we assume that our model was correctly specified. But it is not necessarily true that although on our side we make sure that it is correctly specified, but in reality we misjudged, and there was misperception that led us to use a wrong functional form. So when this is the situation that we are unable to select the appropriate, correct and the right model, then there is a problem of heteroscedasticity. For example, if you are measuring the demand, if you demand of a commodity, and you take some of the variable, for example, you take only the price, and you ignore the price of substitutes and the complements, your model becomes misspecified, and you may face the problem of heteroscedasticity. So I would like to show this. For example, if I say that your model was this quadratic, but you run the simple regression beta 1 plus beta 2x plus ui. So this is the problem. The reality was that there was the nonlinear relationship between the variable, but unfortunately, and due to lack of expertise, skill, or you can say simply the negligence, or even I can go one step further for the easiness, you use this linear form, and as your model is misspecified, there is immediately chances of and the probability of entering heteroscedasticity in your model. So I was giving the example of, for example, this is the quantity demand. It is a function of many variable, and if I say that you only choose one of the variable, and your model became that qd is equal to beta 1, that is the intercept, and minus there is a regulator beta 2 p plus ui. But you ignored many variables, the substitute prices, substitute, and the complement. Substitutes and complements also affect. For example, that you can see you are looking the demand of U phone SIMs, and there are substitutes for this, the Telenor, the Jazz, and the you can say the other mobile networks. If other mobile network, for example Telenor, decreases the price, you will come to know that immediately there will be decrease in the demand of the U phone SIMs, because these are the substitute. So when the simple, at the end I would like to say simply that if there is misspecification, any kind of misspecification, there was some necessary variable you could not include. You took the there was a linear non-linear relationship, you assume the linear relationship. Whatever the source of misspecification, there are the chances and the probability of this this heteroscedasticity. This is the sixth reason. Skewness. Skewness in the distribution of one or more regressor included in the model. Skewness means that it is not normally distributed. So what this means, if you look at the reality, you will come to know that many of the observation, many of the variables are skewed. So what this means, for example, economic variables such as income and wealth. If you see the income and wealth, income in Pakistan, I will not go into the other countries, you can see the income in Pakistan is concentrated on few hands, and many of the peoples are not having such a large amount of income. So this distribution of income, or similarly wealth, similarly if I go to the education, you can say the education is have a different distribution in the cities, particularly the cities of Lahore, Islamabad and Rawalpindi and Karachi, as compared to the rural areas of southern Punjab and particularly the rural areas of the Balochistan. So this is the situation. If there is skewness, then there is also the probability, because your regressors are not normally distributed. There is at some side there is concentration, and you are looking that there is a problem of heteroscedasticity. The very good example are the income, wealth and the education. Many other variables can be of this kind, but this is the situation. For example, if we like to see the facilities of the population of Pakistan, what that they are enjoying, you will see that in the cities people are enjoying more facilities as compared to the people who are residing in the far-flung areas of this Pakistan. The other reasons, still this is the seventh reason, and there may be other reason. This is not the final touch, you can say. There may be some other reason. The first reason is incorrect data transformation. If you remember, go back, when we were solving the problem of multicollinearity, one of the this remedial measure was that the transform of data. I remember, for example, we said that if data is in this kind, y is equal to beta 1 plus beta 2 x2 plus beta 3 x3. So what was this? For example, this was the GDP, this was the taxes, and I say this was the saving. So if this is the situation, if we divide all these variables by population, you will come to know that the population, now you have transformed your variables into per capita. This is the total population and it is divided. So if this is the transformation, it is a solution to one of the problem, but at the same time it is the, you can say, the reason behind creating another problem. So this, if this is the situation, if we transform the data, there is another problem for this. So if I say that, if you remember, this was yt was beta 1 plus beta 2 x2 plus beta 3 x3, and what we did, this was the yt minus 1 it was equal to beta 1 plus beta 2 x2 t minus 1 plus beta 3 x3 t minus 1. So if we take yt minus 1, this is the first difference transformation of the variable. It will become beta 1 minus beta 1 plus beta 2 x2 t minus beta 2 x2 t minus 1 plus beta 3 x3 t minus beta 3 x3 t minus 1. So this was the transformation. You can go one step further. To just you can say the simplify this this expression. So what was this? That if there is transformation, it can lead to another problem. And the second part of this is that the other issue that I think I discussed in detail, that there in the misspecification. The misspecification was that you ignored a very important variable, or on the other hand side, I can say that you include a variable that was nothing to do with your explanation of the dependent variable. The situation is there that you need linear model, but you use log linear, and you know what was the semi-log, what was the double log, and in this case there is a problem of heteroscedasticity. So this was some of the reasons, the sources from where it can emerge into the data. Implication of heteroscedasticity. For example, I would like to say that if we see that our disease is not dangerous, we take it easy. For example, if I say the multicollinearity, if there is not a very high multicollinearity, it is not a very, very big issue. But if look at the people or the patients, and we are a human being, if we come to know, if we diagnose unfortunately a disease that is very dangerous, so we immediately become cautious. So that's why I am giving here you that what are the repercussions, the consequences and the implications of the heteroscedasticity. After knowing the implication, it is up to you whether you decide that whether you ignore it or you take it seriously. The ball is in your court. OLS is still unbiased. I have not used the word below here. I have said that it is still unbiased, but it is no more below. What is the below? Best linear unbiased. So this is fulfilling this property, and this property is that expected value of beta 2 hat. I am always writing beta 2 hat. You can write any type of beta 1 up to beta n. So this is equal to true beta, as we proved in the Monte Carlo experiment. So it means the one property is fulfilled. The other is OLS no longer efficient. This is now the problem, and the problem is that now it is the B is dropped. B means best, that among the competitors that a linear OLS method has the potential to produce estimator that have the minimum variance. But now the problem has arisen, and we have seen that now they are not the efficient. Efficient means they have the minimum. They have not the minimum variance. Some other method, for example, the maximum likelihood, the generalized least square, the weighted least square, they may produce the estimator that have the minimum variance. What will happen if this is not the minimum variance? Immediately estimated standard error will be incorrect as your standard errors, because now it has not the minimum variance, and you collect the standard error from the variance of the parameter. So as this will be, this is C, I mean this is the confidence interval. As your error terms disturbs, your confidence interval also disturbs. And as we are supposing here, look at this confidence interval. For example, this is the acceptance region within these two vertical lines. I say 95% acceptance region. So what will happen? For example, here I will say that our parameters are below. So now what happens if it becomes not efficient? Its variance will increase, and look at this. This may increase this acceptance region. So what will be happen? you will not be able to reject the null hypothesis, t statistic will become insignificant, and you will be facing the problem of hypothesis testing. The solution is, in this cases, the solution is weighted least square and the generalized least square. We will be talking about more about the weighted least square, and we will be looking that if this is the position situation of heteroscedasticity and OLS are producing the estimators that are no more efficient, the weighted least square has the potential to produce the estimator that are still below or they are the minimum variance. Test for heteroscedasticity. How to test that there is heteroscedasticity? Because I would like to repeat, I would not like to shy repeating, because if you are unable to know that the problem exists in your data, then how will you come to know that you are going to take measures to eliminate, or you can say to get rid of this problem? So like multicollinearity, as in that was the first problem of the classical linear regression model, there are no hard and fast rule, no rule of thumb that we only push the button, we come to know that there is a problem of heteroscedasticity. It is also based on your expertise, your previous knowledge, your skill, and your seriousness about your analysis that will enable you to find that whether there is a problem of heteroscedasticity or not. So few rules of thumb. At this stage we can present only a few rule of thumbs. If you follow this rule of thumb, most likely that you will be able to diagnose these cases. Most of the time it is a matter, heteroscedasticity is a matter of intuition, that you have now an educated guess, you have some of the intuition. For example, if you are looking a match and you have intuition and you can predict the values. Similarly, if you know about the cross-sectional data, time series, pooled data, longitudinal data, and you have come many times done analysis on these data, you are in a position to tell that in which kind of data there is more likelihood that the problem of this heteroscedasticity may appear. Educated guess means that you are a good expertise, and most of the time your guess are wise. They are not random. Most of the time you are, and your prior empirical experience. Experience has no alternate. Always experience are there, and they have the value, they have the weightage. You can't say whatever you are talented, but there is no alternate to experience. So prior model empirical experience, as I said, that you worked on many kinds of data and you came with this, and you are now in a position to tell in which kind of data there is a problem. And then there is a sheer speculation. This is now the randomness. You have nothing to do. You have no experience. You have no, you can say, intuition. And by the way, I am supposing that your guess was never educated guess, and you are in the habit of predicting things in a random ways. So what will happen? That sheer speculation. Only that you can suspiciously looking at the data, and you should see that if you should assume that there is the heteroscedasticity and test. If it is not, you are very happy, and if it is there, then you will be thinking that you are the correcting measure on your hand. Two approaches to detect the heteroscedasticity. First is the informal methods that are based on the intuition and what kinds of thing. The first is the nature of the problem, the sensitivity, the nature, you can say, what is the problem in itself, that will tell you that whether there is a problem of this heteroscedasticity. Because going back to multicollinearity, if I see that there is some physical constraint in the data, I would guess, I would suspect that there is a problem of multicollinearity. But here I am saying that if the nature of the problem under consideration suggests whether heteroscedasticity is likely to be encountered. Now I am going to tell you a rule of thumb that if there is cross-sectional data, in cross-sectional data you see that there is one time and there is heteroscedastic unit. For example, if I want to see the growth rate of different countries in 2012, for example, I see Pakistan and as compared to, I say, the Switzerland. These two entities are now totally different. What the different one is the developing country, and that is the Pakistan, and the other is that is the Switzerland, the most developed country. It's one of the most developed countries. So there is heteroscedasticity. So in the cross-sectional, there is a huge probability that there will be the problem of heteroscedasticity. So whenever there is a cross-sectional data, presume and before your assumption that there is a heteroscedasticity, but it is never 100% that every time there is heteroscedasticity. For example, if your different entities are objective as not much different homogeneous, then there is a very, very small probability that there will be problem of heteroscedasticity. So one rule is that whenever you are confronting with the data that is the cross-sectional, the problem of heteroscedasticity is a rule there. The informal methods continues, the graphical methods. Graphs, if you remember, in the first or second lecture, I emphasized that every time you should start from the graphs. What is this? Graphs give you a very clear picture, and the graphical picture, what we do, we run the regression by using the OLS estimator, assuming there is not heteroscedasticity. We have the data, we run the OLS regression, and we assume that there is no heteroscedasticity. There are, in other words, indirectly you say that there is homoscedasticity, the variance of the error term is constant. So now you have completed your analysis, but now you have to check that whether your assumption was right. And what you will do, now you will plot the residual square ui hat against yi hat. So if I want to show that, what is this? For example, if you run this regression, this is y, that is the consumption is equal to beta 1 plus beta 2 x. X is now income. I am not going in many other example because this is the simplest example. Demand is simplest and the consumption and income, it is related to your everyday life. And this is the consumption. So what this says, you have the data and you run the regression. And you got the result. So what happened, you at the end, you got the ui and you know that it is yi minus yi hat. This is the error term, the observed term, that is the real or the original term between your estimation. So this is the situation, and what will be you doing when you will get this residual? You will be getting a series of, for example, if you look at this, this is the y series, this is the x, so this is 3, I am supposing the values 10, 6, 20 and 7, I say that this is 25. So I think you estimated and you got yi hat. So this is yi hat. For example, yi hat is 12, 25 and 20 here. Then you will be getting ui hat. The difference between y and yi hat, this is minus 9. This is minus 19 and this is minus 13. So I would like to take ui square here. If I get the ui square, I can plot it against two variables. Both will be giving the same result if there is bivariate regression model. So what is this? If you look at this diagram, here is ui hat square as we have taken. For example, if I take the square, it will become 81, it will become less than 400, and this is 169, and this is something here I am ignoring because I am not able to get the exact value and I am not using the calculator right this time. So what is this? This is the position, and if I plot these residual against this column, for example, this column and this column I am presenting with each other. On one side is this is, if you look at this, there is not a systematic pattern between the ui hat square and the yi hat. But if you see at this example, you are see that there is a systematic relationship between the error term square and the estimated terms. Similarly, there is a very simple linear relationship. There is, you can say, nonlinear, and there is another nonlinear relationship. So what this means, that if at this stage there is no heteroscedasticity, there is homoscedasticity, but in other cases you can say that there is heteroscedasticity. Why we plot this? Our purpose is to estimated mean value of y is systematically related to the square residual. Now you can see that it is, we were interested to test it, that whether it is systematically related to the estimated term, mean value of the estimated term, and we came to know that except of this a, then there was every term the relationship between the residual sum of square and this yi hat is some systematic. If I would like to show you that this is, that if I want to plot this, I would like to plot it here. Rather than now yi hat, I am plotting the residual sum of square against the independent variable, that is the xi. So if this is the situation, this is ui hat square and this is xi. If I think that this is the relationship between this, you will immediately guess that the xi and this is, if I take this limit also, that the xi and this ui are related with the systematic way. And if I see this is the situation, that this is, that there is no systematic trend, this is ui hat square and this is xi. So this is the you can say the portrait of that there is no heteroscedasticity, this is homoscedastic, and this is hetero. So this was the informal method, that was the second. First was the nature of the problem, the other is that the graphical representation. Now we are going more mechanical and technical, and we are entering that we want some formal methods. In the formal method, the first is the Park test. Very interesting this is, that what is the Park test? It is a two-stage procedure. In the first step, what we will be doing, we will be running the OLS regression disregarding the heteroscedasticity question. We will close our eyes on the problem of heteroscedasticity. We will assume that there is no heteroscedasticity, and we will run the regression. And as we will run the regression, the purpose of the regression is to get the ui hat. Now I need not to tell that what is the ui hat, because you know this is the miss of the your target, that your target was there, you fired and it hit somewhere rather than the target, and now the distance between your target and your hit is called the error. So this is the we first run the regression from this, and now in the second stage we run the regression, this regression. This is very interesting, that how we came to know that this is the regression, that how we will run this regression. Look at this, in the Park test it is assumed that this is sigma I square, that is the unknown, is equal to sigma square x power beta 1 e power v, now I will say it v, just to differentiate. This is also error term, u, e, v, this is the error term, this is that the e power vi. So if I take log on both sides, this will become ln sigma square, this will become ln sigma square I plus beta 1 ln xi plus vi. Why vi? The natural log of e is equal to 1. So this is the situation. Now you can see that these are not directly measurable. So what we will be seeing, we will be estimating it from ln ui hat square, and many times we have done it previously, that if there is true parameter in our regression, there is some alternate, or you can say the representative in the sample. For example, beta 1, if we are interested, there is alternative beta 1 hat. If there is sigma square, the error of the variance, there is ui hat square. So now what are this? We assume, just for differentiating it here, that this is lni, this is now alpha, and we run this regression. I think it is a good time to show it here. For example, this was the situation that this is the sigma square I is equal to sigma square I xi power beta e power v. So if I take log on this, this is sigma square I is equal to ln sigma square I plus this is beta 1 plus beta 1 xi ln xi plus vi or ui. So now I would like to just write it that this is ln ui hat square is equal to alpha, this whole is now alpha, plus you can say beta 1 ln xi plus vi. So now we have run this regression. The first was we immediately run the regression OLS disregarding the heteroscedasticity, simple regression, heteroscedasticity whatsoever. So what was the simple? Y is equal to beta 1 plus beta 2 xi. We run this regression by OLS, and we assume we got the values of ui hat, and then we run this regression. Now how we will come to know that where there is heteroscedasticity or not? If we test, now look at the rule of thumb. If we test that the beta, this is the slope coefficient, now this is the beta, if it turns out statistically significant, for example what this means, that if we test that it is equal to 0 and we reject the null hypothesis, it becomes statistically significant. If this is statistically significant, then there is the problem of heteroscedasticity in the data, because we are assuming that there is no heteroscedasticity. This was our null hypothesis, and as it is significant, we reject that there was no heteroscedasticity in the model, and indirectly we are saying that we have accepted that there is heteroscedasticity in the data. If it turns out to be insignificant, for example, if it is insignificant, we are very happy that now we have rejected our null hypothesis. We are unable to reject our null hypothesis, and I will be writing that what was our null hypothesis. So look at this. If I give to, like, this was H0, no heteroscedasticity, I would like to save time, heteroscedasticity in the model, in the data, and H1 is there is hetero in the data. Look at this, the previous model, if you remember, that was ln ui hat square that we estimated is equal to alpha plus beta 1 ln xi plus ui. For example, now I estimate and it becomes ln ui hat square is equal to 50 plus 0.75 ln xi. This is the situation, and now I suppose further that its standard error is 4.3. This is just supposition. Do not think that these are values coming from something special. These are just supposition. You can suppose any of the value. It is just to give you the its clear impact and clear idea that what is this. So this is 4.3, and I say that the standard error of this beta is equal to 0.97. And I further assume that this is the t statistics and this is 3.7 and this is the t statistics 4.5. And as the t statistics is greater than 2 as a rule of thumb, assuming other assumptions, so we will say that this beta 1 is now statistically significant. And if you go to your rule of thumb, you will come to know that if beta is statistically significant, look at these two words, if this becomes statistically significant, we say that there is heteroscedasticity because we reject the null hypothesis. Our null hypothesis is H0 is that no heteroscedasticity, and as we have brought enough evidence against our null hypothesis and we have rejected it and we said that there is a problem of heteroscedasticity. So this was the first formal method. The second formal method, that is a very similar to this, only very small different, that is the Gleiser test. The same procedure, the first step is the same. The Gleiser test is similar to spirit in the park test after obtaining the UI hat from the OLS regression. Same, उसी तरह आप उसको run करेंगे, you will come up with the UI hat. These are the residual. And rather than now taking UI hat square, the Gleiser adopted another technique. And what was the technique? He said that regressing the value, absolute value of UI hat, rather than taking the square. If you look at all these functions, this is the absolute of value of UI hat, which means that if there is any of the minus value, we will be treating it as a positive value. On X, now what will be Gleiser just regressing the absolute value of UI on X variable. Look at this, X variable is on this side. That is thought to be closely associated with summation sigma I hat. Gleiser used the following functional form. These are the functional form. And the rule of thumb is rule of thumb is again the same, that if this slope coefficient, that is your beta 2 here, if it is statistically, if beta slope coefficient is statistically significant, then there is a problem of heteroscedasticity. You will again reject this null hypothesis because we assume that there is no heteroscedasticity. So this is, but in this case you can immediately guess some of the problem. The problem is immediately there, that there is a problem that sometimes this error term is not following the assumption that we make about this. If this is not following the assumption, for example, if I say that is our assumption is that it is normally distributed, if it is not normally distributed, I will be saying that this is in the function and it is not following the distribution, so it may create problem. The more major problem you can see now here, you can see that in this situation the model has become non-linear even in the shape of parameter. Our basic assumption is violated. So there is a problem with this, but sometimes in normal cases this is also a very good measure. So I think I would like to, rather than going further, I would like to complete this, that what was the heteroscedasticity and what were its consequences and what are this. So I am going to give a brief summary of this today lecture. If you remember, we are talking about today about the heteroscedasticity. What the heteroscedasticity is, simply speaking, that the variance of the error term is not constant over time. It is either increasing, it is either decreasing. As compared to the multicollinearity, this is a very, very serious problem. In multicollinearity, if you remember, our estimator were below, best linear unbiased. But in case of heteroscedasticity, the OLS estimator, that for example they are beta 1 hat and beta 2 hat, they are no more efficient. Although they are unbiased, but now they are not efficient. Efficient means they have not no minimum variance. And how we can get the minimum variance? We have other method, for example the weighted least square. We will be talking about in the next lecture about this. So what is the nature of this heteroscedasticity? I explained that the variance of the error term is not constant. From where it comes, how it comes into the data, so that if we know that what are by which way we are we get disease, we will be not eating those foods and we will be avoiding this. So from which it comes, it is the problem of the cross-sectional data. If the cross-sectional data, you should be, you can say that this is the there. From other it comes that in reality many of the variables have the skewed distribution. The very good example could be the income, the wealth, and many others. The other may be that your model is misspecified. If you are if you are not able to specify your model in a very correct way, then you may be facing some of the problem over time. The other reason from where this heteroscedasticity may come is that improvement, that as there is improvement in the data collection, there is improvement, and this variance keeps on decreasing. The other is the learning error learning problem. For example, if you look mature and you are mature, and if we take your behavior 10 years before, now you will come to know you have become more, you can say, the serious or more accurate, precise and concrete. For example, if you are typing a page in the first hour, you are making more mistakes. In the next hour, there is the probability that you are making that. The other source may be that your discretion increases or decreases. For example, if I am looking at your saving behavior, when your income is very small, there is a very small spread. But because your discretion is very low, but as your income increases, you becomes the tycoon, business tycoon, and I hope you are becoming a good business tycoon in the favor of the country, not just for yourself. So then there is a problem of, you can say, the discretion, your discretion increases and the error increases. The other was that there is a improvement in the data collection. Banks are using, for example, nowadays the computers, and you can see that there is improvement in the quality. The next purpose, our purpose was that how to detect it. The first are, as usual, the formal method. The first formal method, that by intuition you should be aware of this. This intuition comes from experience, skill, expertise, and I think as you are working nowadays on the e-views and you will be getting some expertise on it, you will come to know that in which data you are immediately suspect that there is a problem of heteroscedasticity. Then there were the graphical representation, very simple, that you run the regression ignoring everything, even the heteroscedasticity problem. You get the residual sum of square. Those residual sum of square you plot against either the x independent variable, or you may plot it against the yi hat. If it is showing the residual and the yi hat are showing some systematic problem trend, then you should be suspicious that there is a problem of heteroscedasticity. And if they are not showing any of the trend, then there is no problem of heteroscedasticity, there is homoscedasticity. Then we jump towards that we need some formal method. It is something abstract, that is the informal method, but it gives us some clue. These are not useless, these are useful because it gives some hint, and it increase our curiosity about looking the problem into a more further detail. The first was that we studies about, that was the test, we called it, that was the Park test. Park test is very simple. Again, run the regression. and now run the regression. After running the regression, get the residual sum of square and run these residual sum of square on an specified model as I have explained. And if the beta 2 hat, that is the slope coefficient, if it is significant, then there is the problem of heteroscedasticity, and there was, you can say, the replication of the Park test, that is the Gleiser test, that shows rather than taking the ui hat square, you take the absolute value of ui hat and you run these kind of models, and ultimately you come to know that whether if your slope coefficients are significant, you say that there is a problem of heteroscedasticity, otherwise there is no problem. Hopefully we will meet in the next lecture. Until, take care and Allah Hafiz.